Well, hello everyone. My name's Shaun and I wanted to talk to you today about a project that I've been working on that's to do with quantum physics. What I'm interested in is whether the quantum realm is actually bigger than we think. So what then is quantum theory? Now we know that quantum theory already has many interpretations. The typical interpretation that most people learn in university is the Copenhagen model, but there are other interpretations too of quantum physics. Now the problem with interpretations is that's what they are. They're interpretations. You can't really separate them. In actual fact, the physicist David Merman once quipped that new interpretations appear every year. But because they can't be disproven, none of them seem to disappear. And other people think that interpretation doesn't matter anyway, because what we know about quantum physics is it works. The mathematics works, it makes predictions, it explains things. And some physicists just use the phrase shut up and calculate, meaning there's no point in thinking about it. It works, use it, don't worry too much about what it actually is. So it seems then that we don't really know what quantum physics is, but we know that it works. Quantum appears to be the physics of the very, very small, which is the diametric opposite to relativity that appears to be the physics of the very, very large. So why the small scale? Are there any examples already out there where quantum physics appears to apply to the macro world? Well, there's been some suggestions of macroscopic quantum phenomena. One, for example, is the Necker cube. If you look at the Necker cube is a two-dimensional drawing that when animated appears to rotate in two different directions. And if you stare hard enough and concentrate hard enough, you can actually reverse the rotation of the Necker cube. So we have a clockwise and an anti-clockwise rotation happening at the same time. Is this superposition of two different states, the state of rotating clockwise and the state of rotating anti-clockwise? It's food for thought. Another such example is the Lissajous curve, if I'm pronouncing that right. Now the Lissajous curve is also interesting because if you look at this, it appears to rotate around a vertical axis. And if you concentrate hard on this too, it also appears to rotate around a horizontal axis. And again, we talk about superposition of two states. This 3D model of a Lissajous curve is being rolled on the table around a horizontal axis. And you can see as you roll, suddenly it appears as though it's rotating around a vertical axis. Again, is that in a superposition of two states? I don't know, but this is some of the things that physicists and philosophers are thinking about. So the third example is cognition. Now, when I talk about cognition, I'm not talking about the way that the brain works. So there's no suggestion here that the brain is a quantum computer. But there are some interesting things about the way that we make decisions, and the decisions that we make aren't always explained by normal probability theory. And it makes an interesting thought experiment to try and figure out what really this quantum physics thing's all about. This all leads back to a phenomenon that was discovered in psychology that's called the Conjunction Fallacy. Now, Conjunction Fallacy can be demonstrated by a problem known as the Linda problem. Now, Linda is 31 years old, she's single, she's outspoken, and she's very bright. She majored in philosophy, and as a student, she was deeply concerned with issues such as discrimination and social injustice. She also participated in anti-nuclear demonstrations. Now, the questions about Linda are this: which is more probable? One, that Linda is a banker, or two, Linda is both a banker and a feminist. Now, when this question was asked to a cohort of people, something unusual was found. Most people answered question two, that Linda was most probably a feminist and a bank teller. Now, there's a problem with that answer. You see, we can represent the possible different answers in kind of a Venn diagram. On the left-hand side, we have a blue circle, and that represents the probability that Linda is a banker. On the right hand side, we've got this kind of mustard coloured circle, and that's a probability that Linda is a feminist. Now the sizes are a bit arbitrary here. If it was bigger, it would suggest that there was more probability she was one thing than the other. Now when these two circles come together, where they intersect in this Venn diagram, that is the probability that Linda is both a banker and a feminist. So that's called the intersect. Now what's interesting is if you look at this Venn diagram that represents classical probability in classical probability space, the probability that Linda is both a banker and a feminist is always going to be smaller or the same size as the probability that Linda is a banker. It cannot be larger because it's the intersect. That intersect is always going to be a subset of the probability that she's a banker. So classical probability theory cannot explain why the majority of people believe that it's more probable that Linda is a banker and a feminist. So this logical fallacy that people come up with when they are making decisions is known as the conjunction fallacy. You might think, well, when have people ever been logical? When do people ever get things right? People use heuristics to try and make decisions, and people don't necessarily follow mathematical logic. Well, no, they don't. But why not? You would think that a calculating machine would follow some kind of mathematical logic. And if not, is there a process behind the heuristic that can be explained with other theories? So, classical probability theory doesn't explain conjunction fallacy very well. But before I move on, I just wanted to show you something that I've done in the meanwhile. So I'm going to go on to explain how quantum probability theory may explain conjunction fallacy better than classical probability theory. But while I was working on this, I also had a classical idea for what might actually be happening when people interpret this problem. So I'm going to explain that first, and then we'll move on to where quantum probability theory might come in. I've kind of nicknamed this my theory of discrete probabilities. So going back to our original example again, on the left we have the blue circle, which is the probability that Linda is a banker. On the right we've got a greener circle this time that represents the probability that Linda is a feminist. And in the middle we have the intersect, which is the probability that she is a banker and a feminist. Now my theory of discrete probabilities makes the assumption that when people make heuristic decisions regarding the Linda problem, they don't see the probability of B, the probability of being a banker, versus the probability of being a banker and a feminist. What they actually do is they see the probability of being a banker minus the probability of being a banker and a feminist versus the probability of being a banker and a feminist. So here on the left now we have the probability of being a banker minus that intersect, and in the middle on the red we have the probability of B intersect F. Now using a little bit of algebra we can reshuffle some of these things around, and we can represent the blue section on the left hand side, this blue crescent now, by the probability of B intersects F prime, and F prime means not F. So this is actually the space of the probability of being a banker intersected with the probability of not being a feminist. Now the conjunction fallacy exists where the probability of being a banker and a feminist is greater or equal to the probability of being a banker and not a feminist. Now again, doing a little bit more algebra with knowledge of Kolmogorov's probability theory, which is classical probability theory, we can rehash both of these equations around so that we can compare them. And I can now represent the conjunction fallacy with this expression. So that is the conditions under which the conjunction fallacy can exist. Now this brings a new term into the equation. We've now got the probability of B line F, and what that means is that is the probability of B given F. So it's a probability that Linda is a banker given that she is a feminist. Now that's a new variable. Now we don't know much about that variable at this point, but we do know the probability of her being a banker is somewhere between 0 and 1. We also know that the intersect of being a banker and a feminist is going to be smaller or equal to the probability of being a banker. Now, knowing those two things, we can actually set some limits on what the range is of the probability of being a banker given that you're a feminist. And the limits of this new variable, the probability of being a banker given that you're a feminist, exists in the range of 0 to the probability of being a banker, using those expressions. So now we've got something that we can actually plot in a graph. And you'll see here in this animation, you can't see the slider move at the top, but you can see the value at the top right hand side. The probability that Linda is a banker given she's a feminist, we're going to have a look at that range, and we're going to see as that varies we can actually satisfy the conditions of the conjunction fallacy. So anywhere under the curve is where those conditions are met. Here's a set of graphs. You can see that in actual fact using this theory conjunction fallacy can exist. So perhaps then that is an explanation behind conjunction fallacy. The thing is though, this brings me to think about this new variable. This new variable is a probability of B given F. The probability that Linda is a banker given she's a feminist. Now somehow these are two different variables together that act on each other. That's kind of an interference. Now interference reminds me of something. Do you remember this experiment? That's right, I think anybody who's done any basic physics knows the double slit experiment. And this is where two paths of light pass through two slits and interfere with each other and produce a diffraction pattern on the back. So perhaps then the reason that we don't come up with answers that should be explained by a normal probability theory, perhaps that somehow has something to do with interference. So I want to think about an experiment that might explain interference of thought and decision making. So what I want to do is I want to set the state for this problem. Now the state is set by the initial story about Linda. Linda is 31 years old, she's single, she's very bright, she majored in philosophy. As a student, she was deeply concerned with the issues of discrimination and social injustice, and she also participated in anti-nuclear demonstrations. That sets the state S for Linda. So let's replace that light bulb from the dual slit experiment with this initial starting state S. So in this experiment, we have two slits, and one slit represents Linda being a feminist. The other slit at the bottom, F prime, represents Linda not being a feminist. On the second wall, we've got B, which represents a probability that Linda is a banker. We've got B prime that represents the probability that Linda is not a banker. So basically we have two paths. Don't worry too much about the Dirac notation if that's not your thing. But we have two paths. We've got this orange path and we have the blue path. Now, how do these paths represent the decisions that are made by us? Well, it's fairly simple. The first thing is the sum of the two paths is going to equal the probability that Linda is a banker. How does that work? Well, one path is the probability that she's a feminist and a banker, and the other path is a probability that she's not a feminist and a banker. So if we add both paths together, we get the probability that Linda's a banker. However, if we put our hand over the bottom slit, we now get the probability she is both a feminist and a banker. So we have two ways that we can represent the equations that we need. So before I go on to the next bit, I just want to talk a little bit about the Born rule. And it was Max Born that suggested you could describe light with a wave function, and if you took the square of the modulus of that wave function, it would give you the probability of actually finding that particle in a position or with a certain momentum, whatever the wave function is being used to describe. Now, a typical wave function for light would be a complex exponential. A complex exponential is interesting. So if you look at a function such as a e I theta, you get two parts to it. You get the real part and the imaginary part, but they're sinusoidal waves. But if you take the square of that function, then you actually get the number 1. This is great. So we have a function that has wave-like properties that when it's squared comes up with a probability, and waves are then able to interfere with one another. So if you take a wave function that describes one path and a wave function that describes another path, those two wave functions can constructively and destructively interfere. So you can see here in the square diagram, I've got a series of sinusoidal lines. Now, the blue line is going to represent the blue function from the graph, the orange line, the orange. The solid lines are the real parts, the dotted lines are the imaginary part. And what I'm doing with this little graph here is I'm just changing the phase between the orange and the blue line to go from them being completely in phase to them going out of phase by 180 degrees and coming into phase again. And you'll see the difference, what that does to the overall wave function on the green line at the top. Now the green line has just been shifted away, it's not actually of the right value, I've just moved it up so it's clear of the other lines and makes it clear. But you can see as they interfere they will give a different pattern. Going back to our experiment then, so we have the two paths. Two paths added together give us probability of B, the probability of Linda is a banker. If I cover up the slit F prime, the probability that she's not a banker, then the orange path that I end up with then is the probability she is both a feminist and a banker. So once again doing a little bit of algebra. So again, remember, conjunction fallacy exists where the probability of being a banker subtracted from the probability of being a banker and a feminist given state S is greater or equal to 0. So now we've got a condition for the conjunction fallacy using interference. This is a little bit more quantum. Now, all those kind of workings looking at the double slit experiment when it comes to describing the Linda problem, this has kind of been done in a more eloquent way. We can do this using Dirac notation. Let's start again with the initial state. Let's say that S is the state vector, because we're now going to talk about state vectors in Hilbert space, for those of you who've come across these before. Now we set S as the state vector. The state vector is this green line, and this green line is the initial state of whether she's a banker or not a banker. Now the same state vector could also be used to represent whether she's a feminist or not a feminist. Now if we align those state vectors, because they are the same, then we get this diagram. From the diagram we can see the probability in Hilbert space that Linda is a banker. You can see the blue thick block line is actually the amount of the state vector that projects on the banker line. Now if you look at Linda being a banker and a feminist, the first thing that we do is we have to project from the state vector onto the axis describing whether she's a feminist, and you'll see that that red line hits the axis. But then we also have to project across from there now to banker. That gives us the overall probability that she's both a banker and a feminist. Here is a representation in Hilbert space looking at those state vectors that we put in the initial diagram when we were looking at the double slit experiment, which shows, given the right initial states, that it is possible to meet the conjunction fallacy for the red line, which is the intersect, which is a probability of being a banker and a feminist, where that is greater than the blue line, that's a probability of just being a banker. So in Hilbert space we can demonstrate using quantum probability that conjunction fallacy is possible. So that's where we are so far. Thank you very much to those of you who have made it this far, and hopefully I'll be able to bring out another one of these videos which will tell you where we've moved to next. Thank you for watching.